So if I can get your attention, please. I'd like to thank all of you for coming. We don't do this very often. We do it on, pretty special occasions when we've got some really interesting stories to tell. We've done it with, say, the British Antarctic Survey. Now we get Joe Mascaro from Planet. I'm Paul Morin. I'm director of the Polar Geospatial Center downstairs without any windows. I just want to point that out. All you guys from I&E, you get the windows. We don't. So, the Polar Geospatial Center does high-resolution commercial remote sensing. We provide geospatial services to, primarily NSFPIs, and we're very, very familiar with this commercial world of high-resolution imagery, and we've been watching Planet Labs and now Planet basically since the beginning. We've got access to 3 satellites at basically about a foot resolution, maybe a little more. But the idea that you could image the whole planet at about 3 or 4 meter resolution every day is a game changer. They're also, as a company, they're just built differently. In downstairs in PGC, we were built very much like a startup, where we're thinking exactly who we're serving and how we're serving it and how we're doing it. Planet is very much a startup, and it has a startup mentality. And the result of that is what you're about to see, which is this groundbreaking way of just seeing everywhere all the time. And then having the organizational infrastructure and the expertise to do this, from source to sink. About the only thing they don't do is they don't build rockets. But they do pretty much every other piece of this. We were talking the other day that, with the satellites we use, there's specific tasking software that comes from this company, and you're going, yeah, we're doing our own. Okay. So they really are doing the pieces. And Joe is the director of academic programs at Planet. He's done all kinds of things, including science writing for the New York Times. You're a PhD in ecology, and you worked here before.
I did.
And you got to talk.
I worked at Cedar Creek for 2 summers, so I'm sure many of you have spent some time there.
So you wouldn't know it by the tie, but he's one of us. And it's Joe's job to engage us. And I just want to say thank you for coming. And
thanks, Paul.
yeah, thank you.
I just turned on this mic. I tend to have a pretty loud voice. We're doing this for the recording, but is it booming back there? Is it terrifying? Okay. First of all, thank you, Paul, for hosting us, and thanks to Polar Geospatial. I also wanted to say that my colleague and boss, Andrew Zolli, is here. He's also from Planet, but he lives just a few blocks away. So we're delighted to have Andrew. Andrew is the Vice President of Impact at Planet, which is the team that I sit in. And so we're doing many initiatives around impacting the world, and I would encourage you to talk to Andrew about some of the other ones that I don't spend much time on today. I want to start with just a discussion of how aerospace has worked in recent history. This is Landsat 7. It's relatively typical of large Earth observation missions. This is about $1 billion program. And as many of you know, when Landsat 7 got to space, it was only about 3 years before the scanline corrector broke, resulting in an incomplete data retrieval that continues today. They were unable to repair it. And so when you have all of your assets or your mission tied up in one instrument, you run the risk of that type of thing. I want to talk about another mission specifically. Just before I do, does anyone in this room work on the Orbiting Carbon Observatory? Oh, excellent, because I'm going to present some facts and figures, and I don't want to be... Okay, so this was a mission that was selected by NASA in 2002. This basically was NASA saying, we need to measure carbon dioxide concentrations in the atmosphere from space across the whole atmosphere of the planet. I think we can all agree that that was a vital scientific decision and a necessary scientific asset. This is not as big as Landsat 7, but it is also a classic sort of large mission. It's relatively expensive. It's about a $270 million mission, spacecraft plus the rocket. The first launch attempt, which was on a Torres rocket, failed. This rocket, the fairing failed to separate, so it was a little too heavy. It crashed into the Pacific Ocean. But it took 7 years just to get from NASA saying, yes, we're going to do this, to attempting to get it into space. A year later, a follow-on was authorized, and they decided to actually upgrade the rocket and make essentially a clone of the spacecraft. This version, OCO2, out the door, is about $450 million. And it did successfully launch in 2014. In this case, on a Delta II, a ULA rocket. That was an upgrade because they really didn't want to repeat the same failure. They were lucky as well because there have been subsequent Torres rocket failures. What I'm showing you here is the evolution of one particular mission where it took 12 years for that mission to get into space and start producing scientific data. The relevant scientific data is actually the timeline that you're looking at, which is the CO2 concentration of Earth's atmosphere. In those 12 years, 25 parts per million of CO2 were added to the atmosphere. So a fifth of all human emissions to the atmosphere occurred after NASA decided we should fund this measurement device and produce that science for the scientific community until we actually did it. And essentially, that pace of aerospace in the way that the Earth and the Earth systems are changing today is simply not going to work. Our mission at Planet is to image the whole world every day and to make change visible, accessible, and actionable. I'm going to tell you about various fleets of satellites that we now operate to do that. But as I introduce them, I just wanted to start by making you aware of what they are. We have approximately 170 Dove satellites in space. These are 3U CubeSats. They're 10 by 10 by 30 centimeters. You can hold one in your hand quite easily. They only weigh about 4 kilos. We also, in 2014, acquired the Rapid Eye group. This is a group of 5 Earth imaging satellites. They image in 5 spectral bands. The Doves image in 4, but also generally designed for land use, land cover monitoring. And in 2017, we acquired what is called the Terabella team. This was a sort of a companion startup with Planet that was acquired by Google in 2014 and was subsequently acquired by Planet in 2017. So about 60 of the Terabella employees came aboard, and we now have 13 SkySats in space. And these are high-resolution, sub-meter resolution imaging satellites, tasking satellites. The idea for Planet originated with our 3 co-founders who were working together at NASA Ames Research Center with Pete Worden. And they're pictured here along with some of the early members of the team. Actually, the majority of people in this photo are still with the company. This is actually a garage at a place called the Rainbow Mansion. So if you're a Silicon Valley company and you're a private sector startup, you essentially need a garage photo in order to prove your street cred, and here it is. And you can actually see one of the early Dove satellites right here in the photo. The idea originated from this notion that we're developing technological devices in our everyday lives at a pace that is wildly faster than what's happening in aerospace. So you take the 12 years of OCO's development, I don't know, we've been through at least 8 iterations of the iPhone during that period. In fact, it didn't exist in 2002. And so the thought was maybe we can start using some of this existing technology and put it into spacecraft, iterate faster, fail faster, and develop better tools. And so this is the Dove spacecraft today. Actually, a few of those on the right are older iterations of it. But it essentially started in this form, which was, let's put a telescope and a camera into as small of a satellite as we can. And to do so, the founders and the early people in the company were using many pieces of off-the-shelf technology. So for example, this antenna on the upper right is now a piece of metal, but a measure you find from a hardware store. It's a perfect antenna flap. It has its own built-in hinge. So you put it in a deployer and it just pops out. You don't need any moving parts. They also, and in this diagram you can see the purple circles there are batteries. Those were lithium-ion off-the-shelf rechargeable batteries, the kind you'd buy at a hardware store. We've since made some major changes and upgraded the spacecraft. The early panels were terrestrial solar panels designed for use on Earth. We're now using space-rated solar panels. We've made a lot of changes to the antenna. We call this Build 13. This is the most recent, most stable engineering model of the Dove spacecraft. And for a few, the body of the spacecraft, it has essentially 0 components in common with build 8. So as we turned it over, the spacecraft has changed. A thing to point out on this, because I won't be able to show it to you in a different figure, all of our satellites in space have artwork on them. This is a shark here. It's a piece, a carve out from a larger piece about migrating animals, designed to evoke a notion that humans are in the process of migrating into space, to settling space. And Forrest Stearns, who is our art director, who's also on the team that Andrew oversees, has done an amazing job of setting up not only artwork on all these satellites, but actually running a vibrant art program within Planet itself, an artist in residence program. Our manufacturing facility for the Doves, which is in San Francisco at our headquarters, can produce if we press 28 satellites in a week. And so when we're in production in preparation for a launch, if you're there, you'll literally see every few hours a satellite will come out of the factory and go off to an RF chamber for testing. We have flown on 14, I think 15 now, the slide's out of date, successful launches, deploying 270 of these Doves into space. That number is bigger than the number I gave you at the beginning because many of them have since re-entered the Earth's orbit. Earlier versions of the Dove were in the orbit of the space station, which is much closer to the Earth's surface. I'll talk more about orbits momentarily. An interesting thing about this, we have flown with almost everybody. So this is a SpaceX Falcon 9. We've flown on the Falcon 9. We were actually on the in-flight failure, the first failure of the Falcon 9 that happened a couple of years ago. We have flown on a Russian converted ICBM called a we've flown on Soyuz, flown on the we've flown on the orbital AT. One of the greatest things about the changes over the past few years, specifically related to CubeSats, is standardization of deployers and the ability of launch providers and also satellite operators to sell off essentially excess ballast that they have on a rocket. So when you buy a Falcon 9 and you're the primary satellite customer for the Falcon 9, you determine the rocket's flight path and all that sort of stuff. It's virtually never the case that you're exactly at the capacity of the Falcon 9. You're going to have excess capacity. And so companies like us, and also especially academic groups that have been building CubeSats and other kinds of small sats, can benefit from these changes in the space industry really spectacularly. And this has resulted in an explosion of deployment of Earth imaging satellites. We operate a large network of ground stations, and many of those are at the poles because our satellites are in polar orbits. And so those crossing opportunities are much more frequent at the poles. I mentioned the Rapid Eye constellation. Here's a look at these satellites when they were on the ground. Interestingly, the Rapid Eye system, which was deployed in 2008 to space, at the time was really the leader in small sats. This sort of idea of building a smaller satellite that had these really high capabilities had never been done before. And so it was a nice cultural fit to bring the Rapid Eye group into the Planet family. This is early SkySat in production in Palo Alto at the Terabella offices in Mountain View. So I'm going to show you some videos of some of our deployments and activities. So this was an amazing day for us as a company. We launched on this rocket 88 satellites on a single rocket. This is the PSLV out of India. It stands for Polar Satellite Launch Vehicle. Those are solid rocket motors detaching from the main body of the spacecraft. And then those are our Doves being deployed. And although the resolution is not quite as sharp as you might see on a SpaceX webcast, for example, you can see, the time of this video is real time. So, that's how rapidly these things are deployed and spinning out. You notice that they're tumbling. One of the first things we do is to detumble them. And we do that with a mix of different things, but mostly magnetorquers. These are electromagnets. We turn them on. The satellite tries to essentially hug the Earth's magnetic field. And this helps slow the satellites down from their tumble. We have so many satellites in space right now. I apologize if this gives you vertigo. That later the same year, we deployed another 48 satellites on a Soyuz rocket out of the Baikonur Cosmodrome, and that's it launching right there. This is not strictly a video. These are frames captured at the same rate that our Dove satellites do Earth imaging. We commanded the satellite to point at a particular target. And that was the Baikonur Cosmodrome, and so you see that flash of fire. That's the Soyuz rocket lifting off, taking off into space. This is amazing on many, many, many levels, but I want to just stress how amazed we all were at our own mission control team, who decided roughly 5 hours before this pass, we'll just do this. We'll give this a shot. And totally nailed it. It was really incredible. This is what our primary Dove orbit looks like. It's approximately 100 satellites, mostly from that 88 on the PSLV. And they're at a 96-degree inclination, imaging in the descending portion of their orbit. And this is a sun-synchronous orbit, so the areas where they're imaging are essentially always in sunlight. And you can see, like, as though you're driving along Zamboni, depending on which part of the Midwest you really prefer, we're collecting strip after strip after strip of data. So in principle, ideally, these strips of data should be flush at the equator. One of the cool effects of this is that they overlap enormously at the poles, and it's part of the reason that Paul brought us out here to talk to you guys. So this is a simulation that we use, Cesium. This is sort of open source aerospace simulator, and I recorded this yesterday, so this is not real time, but this is what the constellation actually looks like. And this here, this major band of dense satellites, that's our primary sun-synchronous orbit. These are the other 48 that were deployed by Soyuz. These sort of guitar strings over here, those are older space station orbiting satellites that are in the process of deorbiting right now. That is, they're re-entering the Earth's atmosphere. And here I've just turned up the speed, so you can see what this looks like. It's quite spectacular, the density of images. From school, you are the sun. I'm sorry, you're not the sun. The sun is moving with the Earth. Yeah. So you're at a fixed geostation. California looks like. Yeah. Those red dots are some of our ground stations. So, in order to see what things would look like in Paul's world, I did another one of these, but now I've fixed us above Antarctica. So this, where it says Troll here, that's a couple of ground stations we have in Antarctica. This again is the primary sun-synchronous orbit. The additional sun strings are the space station sats, which don't get down to Antarctica. They only get down to 52 degrees south. But there you can see this basically continuous, never-ending stream of polar imaging opportunities with the Dove constellation. Really spectacular. I'm going to show you what some of the data look like. I've pulled a few figures that are from the part of the Earth where people live and not typically the areas that we're studying when we're doing polar science, but it makes it easier to understand the limits and the strengths of the pixels. So this is full resolution Dove imagery. These are petroleum tanks. There's actually a big analytic market in mapping these shadows in these tanks, these drums. They're the kinds that you see all over port cities around the world. You can use the shadow because they have floating lids. So these are tanks where they're full. I didn't realize this until recently. It makes quite a lot of good sense, which is the floating lids are to prevent methane from building up on top of the petroleum, which would cause these to explode. And I'm very curious, it takes a double lid tank in order to confuse satellite-based analytics of petroleum tanks. This is, I believe, the Alameda area, and again, it's a Dove image, and you can see, for example, you see some traffic on the freeway there. You can't quite resolve individual cars, but you can start to resolve or get pretty close to resolve tankers, or excuse me, containers in container shipping. This is a full resolution SkySat image, so that's a railroad yard right there. And here's another one, and I've forgotten where this is. Those worldly people in the audience may know. I think this might be Berlin. The colors are collected at slightly different times, so these little color smears are moving vehicles, and you can actually write an algorithm that pulls out the velocities of those vehicles. And this is a boneyard in the southwest US where we stage decommissioned aircraft for deconstruction. And SkySats are pretty incredible. They are actually unique among commercial sensors in that they're capable of high-resolution, full-motion, panchromatic video from space. This is Taipei. And you can see the parallax. The satellite is looking just like it's looking at a fixed target. And so it's doing this kind of maneuver while it's at about 8 kilometers per second. This is moving traffic. Really exciting opportunities, especially for 3D modeling, potentially, of the kind that Paul and his group work on. So I'm going to tell you a lot about some of the science that people are doing with Planet data, but before I do that, I want to tell you what Planet's core business model is. We are a for-profit commercial company, and importantly, our activities in the commercial sector are actually really highly aligned with what we're doing with scientists. And it simply has to do with the fact that most people are in a stage where there's so much Earth observation imagery or data feeds that they're beginning to write algorithms that need to be sensor agnostic, or they need to be able to jump from Sentinel to Landsat to Planet to Digital Globe in order to execute on their business, but also potentially to do the best science in the world. So we don't see Planet's data feed as competitive with with government Earth observation like Landsat or Sentinel. In fact, it's actually helps level up the kinds of analyses you can do. So here's an example of a data feed integration that we do for Planet, and it relates to parking lots. So many commercial companies have an interest in the density of vehicles in their parking lots around the world. With the SkySat system, we can get pretty close to resolving individual vehicles. So this is a parking lot. I think this one is Alameda as well. So this is full resolution SkySat. It's about 80 centimeters per pixel. So you can see that you're able to count individual cars, even though you can't necessarily tell a Volvo from a Volkswagen. So we produce a count of those cars algorithmically, and then we go and look at the PlanetScope data. Now, coarser resolution at 3.7 meters, we can no longer resolve the individual cars, but we have a pretty good sense of where are cars versus not cars. And then we can correlate those two data sets. We bring them, yeah. Oh, sorry. It's no problem.
That's on there.
How's that? Can you guys still hear me? Better? Okay, so cars at different car detail. With the SkySats, we can see the whole cars. With the PlanetScope, we can get a sense of where the cars are. And then we can build algorithms, basically, first step, put those two data sets together, line them up. How accurate are you able to predict the vehicle density with the PlanetScope resolution, knowing that you have a sort of a validated SkySat observation? So this type of approach is a very simplistic approach, but it is fundamental to many of the things that Planet is doing in its core business in terms of integrating different data feeds and being able to produce insights that are valuable in the marketplace where the end user might not even be interested in the actual pixels, the actual data. What they want is a validated piece of information that they can use. And so next I'm going to tell you about two activities that the impact team works on at Planet. And these are the two areas where I think our work is most relevant to what most of you do, although not exclusively. The first one, and I'll just give a couple of examples, but I want you to be aware of our disaster response activities. Planet participates in an entity called the UN Space Disaster Charter. So we are one of the organizations that may release data, if appropriate, under a humanitarian emergency or a natural disaster. As an example of this, we're in a collaboration with Human Rights Watch right now to work on the welfare of refugees that are leaving Myanmar and entering Bangladesh. This is from a piece that Thomson Reuters put together on this crisis using Planet data. And here, this is PlanetScope data. On the right, they show the beginnings of this camp and then show its growth over just a 3-month period. This is the expansion of this camp. I think, I don't have an act. Do you remember a number of people? I think it's around 100,000.
It went from like 15,000 to 150,000.
Yeah, yeah, so up to 150,000. We couldn't hear Andrew. It's really a horrific situation. With the SkySats, we're able to take a closer look. This highlights one of the most important utilities of having a constellation that is in passive imaging mode all the time and taskable high-resolution assets that can be queued in order to look at areas of interest. We do similar things, or we did a similar type of activity after the hurricane season in the Caribbean. This is actually, by the way, the Planet Explorer. This is a GUI built on top of our API. So this is a piece of, essentially a piece of software that is wrapped around our API, our application program interface, which is both the, it acts as the gateway to our repository of data, and also will communicate with software in whatever custom ways you want to. So this GUI is something you guys could build if you wanted to build something similar or something different. Sorry, I'm talking over this blinking GIF. What you're looking at is this green image there is prior to Hurricane Irma's impact on the British Virgin Islands, and the brown one afterward is shortly thereafter. The vegetation on the island was stripped to the bone. It is actually the case that Caribbean ecosystems are pretty well adapted to these kinds of disturbances. It is less the case that humans are adapted to them. This is a high-resolution SkySat image that was queued in the aftermath of this disaster, and you can see that you're able to identify whether structures have been completely destroyed or what their status is. There's also, it's a little bit hard to see here, but you can see debris in the water, which was a factor in getting marine emergency assistance assets in place. So what I'm going to spend the remainder of the time talking about is some of our collaboration with scientists. So the program that I run at Planet with a small team is called our Education and Research Program. I've left some gorgeous postcards up here. If you need to know how to sign up, just grab one of these before you leave. But I'll also tell you, you can just go to this website. It's go.planet.com/research. This program is exclusively tailored to universities, so you have to have a university affiliation to apply. But if you apply and you just tell us a little bit about what you're working on, what you can get access to is up to 10,000 square kilometers per month of Dove or Rapid Eye data. We have about 1,300 users in this education and research program now. And I want to tell you about this really huge diversity of projects they're working on. One of our first users, he's been working with us for over 2 years prior to the existence of this program, is Andreas Cobb. He's a glaciologist at the University of Oslo. And just 2 weeks ago, he published this major paper in Nature Geosciences concerning this event, which was the collapse of 2 alpine glaciers in Tibet in 2016. There was actually a New York Times feature about this paper the day after it came out. This was a really kind of shocking event. Andy kind of caught me up to speed on the history of this, but basically when it comes to alpine glaciers, there's only one similar event known in modern history, and that happened in Russia in 2002. Here, in July of 2016, this northern glacier sheared down to its bed and erupted into an avalanche. It killed 9 people and a great deal of livestock. And Andy was working relatively shortly thereafter looking at planet imagery and sentinel imagery and other sources of imagery to try and understand what the mechanism of this collapse was. To go back to this figure, this is a key figure from his paper, and it's a planet image taken just 2 days before that first collapse. And what he's annotating here is the deposition of sediment on top of the glacier that came from the bed of the glacier. So essentially, there's some kind of hydrodynamic instability that's pulling sediment through the glacier like a sponge. This was such a smoking gun that they started to see a similar effect in the second glacier. In this case, it was also influenced heavily by sentinel data. His team sent a warning to Chinese authorities, which actually arrived 1 hour after this second glacier collapsed in September. Fortunately, nobody was killed in that event. There was another group working totally independently from Andy's group that also had some ability to, or came close to predicting that collapse. This is really incredibly interesting science from a climate change point of view. I think it's urgent and important science, but it's also really powerful from a predictive point of view when it comes to disaster response and disaster mitigation. A glacier shearing off is clearly now a rare event. We have 3 known in modern history, and you just saw 2 of them. Our ability to predict that is probably still pretty challenged. But if we can start to build our data feeds into predictive tools that could potentially allow for warnings of deformation type events like landslides, mudslides. This would be something incredibly powerful for the scientific community. It's also the immediate aftermath of potential disasters. In this case, a study in New Zealand, also led by Andy Cobb, they utilized planet imagery from before and immediately after the New Zealand earthquake that occurred in 2016. In this case, they were taking planet images and looking at the deformation event. So what you're looking at are vector fields. So there's 2 planet images embedded in each one of these, a before and an after. The blue pixels are pixels that shifted to the east. The red pixels shifted to the west or were stationary. And then the vectors decompose, so the north-south shift is on the figure in the right. And you can see this easily highlights the various faults that were implicated in this particular earthquake. Here they've zoomed in and shown a couple of areas where the fault separation was as sharp as it can get, basically just a totally true strike-slip event. This figure they designed, and I didn't quite understand it, they're putting the vector field now on top of the planet image. And in order to really see it, you have to pull it away. But here is the before and after planet images, and this line right here, this sort of faint gray line, is the actual crack in the surface of the Earth that was created by this deformation event. There was a second fault, and in this case, the deformation event resulted in the seafloor coming out of the ocean. So you see the rupture there, and you can see there's a piece of Earth that was not there prior to the earthquake. This is a photo from the ground. I was told by New Zealand colleagues that there were like lobsters walking around wondering what was going on. What's really instructive about this, in this case, earthquakes, certainly not predictable from imagery. I think I can say that with certainty, at least, well, most types of earthquakes. What's interesting here is because planet images consistently on the Earth's surface, without knowing a priori where an earthquake is going to take place, assuming it's cloud-free, we have the capability to generate these types of maps in the hours after an earthquake and get them to the field, actually deploy them, and have people using them for emergency response. I think it's pretty powerful stuff. There's another person in the program, Bas Altena, also at the University of Oslo, who did something really cool, and he did it with our space station orbiting data, and I'm not sure how well it's going to work in the future, but we were talking with Paul about it a little bit. There's sort of 2 ways to do 3D modeling of an object with cameras. One is photogrammetry, so stereo imaging, where you're imaging from multiple camera positions around the object. A second one that I was not familiar with is called photometric stereo. In this case, you're using the same camera position, but you have many looks at the target under different illumination conditions. And Bas pulled our space station orbiting satellites together in order to do this, because in the orbit of the space station, there were certain situations where we had perhaps as many as a half a dozen or a dozen images of a single target in the same day or within a several day period. So he pulled those together for a particular glacier. And using this photometric stereo, this is just what the images look like. This isn't perfectly well orthoed, but it gives you a sense. You can see the shadows moving around. It almost looks three-dimensional to your naked eye. He was able to pull those together and generate a surface model for this glacier, and actually produce an elevation model for it. I'm really curious, because of the way our orbits work and because of different mix of illumination and crossing time, I'm really interested to see algorithmically how these techniques can be hybridized, or how you can deal with stereo imaging under different mixes of illumination conditions. Another really cool study, and this one was just published in Remote Sensing a couple of months ago. This was work led by Sarah Cooley. She's a postdoc now at Brown. She was at UCLA at the time she was doing this work. Really incredible look at hydrology in northern Alaska. Here, because of Planet's dense time series of data, she was able to track the evolution of Arctic lakes over a super dense time series. So these are individual lakes where she's highlighted the particular day of year, and she could tell you the surface area of that lake. Here's a quick animation that shows you like what the water level changes were like in these lakes over time. Because she can tell which lakes are shrinking and swelling, with the local hydrology, she can tell you which lakes are connected or disconnected from the hydrologic network of this area. So there may be lakes, for example, that are just bucketed out by permafrost and they don't have a connective tissue with the local hydrology. Others fluctuate and pulse with the, say, a nearby river. I thought it was just really excellent science. One that we haven't fully exploited yet, but was pointed out to us by Andy Cobb. As a result of the fact that our orbits, remember at the equator, ideally they should be flush, so they cross heavily at the poles. This is individual tracks of planet images, and these now are, you're seeing two tracks where one satellite is, the first satellite is passing over, and then the next satellite is passing approximately 1 minute behind it. So these two images, which overlap because we're at the poles, have, they're separated by only about 60 seconds in time. And this happened to be during spring thaw in the Arctic, and so Andy is able to see actual ice debris moving in these rivers just over 60 seconds. And he can then, in a straightforward deformation analysis, essentially slap a vector field on there and tell you the velocity of that river. I think when it comes to climate change in the Arctic, this is potentially a really powerful technique, and Planet is collecting an enormous amount of these types of sort of ad hoc overlapping images that could be utilized. Another example, and probably the best work I've seen dealing with planets radiometry, comes from a user in King Abdullah University of Saudi Arabia. His name is Matt McCabe. He's an agriculture scientist, and he has a big group, and they're pretty strong in machine learning. So they are dealing with some of the uniquenesses of planets' radiometry. So, for example, our sensor has a different spectral response to light than the Landsat sensor. That is to say, our red channel is not going to be, it's not going to produce an identical spectral response aimed at the same target as Landsat's red channel on the same day at the same time. And this means that off-the-shelf Landsat-based algorithms, it's not just plug and play. You need to adjust things. So, for instance, this shows you the difference in uncorrected PlanetScope NDVI estimates. That's the Dove sensor, the CubeSat, and Landsat 8. And through this model, Matt and his team are able to stabilize these observations and produce a highly consistent, very stable radiometric feed from the planet constellation. And it allows them to do extraordinarily powerful stuff because now they have a mix of essentially the Landsat spectra. These are like simulated Landsat spectra at the high spatial resolution and high temporal resolution of the Dove satellites. So here's an example of one of their outputs, and I thought this was really, again, when it comes to some kind of spectral work, the most powerful stuff I've seen so far with the Planet CubeSat constellation. These are, I believe this is a maize field in Saudi Arabia. I think it's a maize field. And here they're doing really intensive circular agriculture. So just over, 130 days, there's 4 crops harvested off of one of these fields. So each of these little dips is a crop cycle. What they've done is they've taken the Landsat 8 LAI index, so that's leaf area index. Essentially, it is it's an algorithm that's been around for a while, so many of you have used it already probably, but it's basically leaf area index as predicted by the Landsat spectra. Now, what they did is they relied on many, like thousands of tandem observations between Landsat and Planet in order to align Planet's radiometry and do the same leaf area index prediction. The kicker is that the leaf area index out of Landsat is actually powered in part by Landsat's SWIR band, and Planet does not have a SWIR band. So here they're actually demonstrating that PlanetScope data is sensitive to local leaf area index, the SWIR information being embedded in some other radiometric compartment of the Dove data, if that makes sense. And I thought this was an incredibly powerful output because now what it allows you to do is track leaf area in near real time, day to day, across these fields. The density of PlanetScope data earlier in this particular year is lower because we hadn't deployed all our satellites to space yet. But even here you can see that the Landsat observations in the red squares missed one of the harvests entirely, and they were able to retrieve that from planet data. This also allows them to be extremely sensitive to things like crop health, disease, et cetera. Another area where we're working is in coral reefs. In this case, we've partnered with Greg Asner from the Carnegie Institution for Science. Greg was, in full disclosure, my postdoctoral advisor. Greg's mostly been doing forest work for his career, but he's really moved a lot of his assets to coral reefs. And in this case, we did the first, to my knowledge, the first high-resolution, well, certainly the first planet-resolution study of coral reefs over a large archipelago, in this case, the Spratly Islands. So what we've done here is, this is a planet image on the top right of Swallow Reef, which is the southernmost of the Spratlys. Greg actually went out to the field at Swallow and did underwater photography, and subsequently did classification of different benthic habitat types throughout the reef. And so that final classification output for Swallow is shown in panel D on the bottom right. This, then we were able to extrapolate that out into the Spratly archipelago and essentially make a map of shallow water reef extent at 3.7 meter resolution, which essentially nobody had done before. We had a second portion of the study to evaluate how the expansion of military bases and other geopolitical factors in the Spratly Islands were influencing coral reefs. And unfortunately, while the paper was in review, this reef, which was one of our control reefs called Lad Reef, was dredged by the Vietnamese, probably as a provocation to the Chinese. This is the typical origin of a base expansion. The dredging allows ships to go into the lagoon and be protected from the open sea, opens up new fishing opportunities, et cetera. So unfortunately, it's plausible that Lad Reef in the next couple of years will turn into an airstrip, anti-aircraft battery, and essentially not be a coral reef anymore. Another one worth mentioning, and this one was done with the SkySat system. The SkySat data is not in this academic program yet, but we do have a few users working with it on an experimental basis. This one originates from a Skybox program that was called Skybox for Good. And here, a mix of collaborators working with the SkySat data. Meha Jain is at University of Michigan now. She was working with Marshall and David at Stanford a few years ago. Marshall Burke and David LaBelle are at Stanford. They do a mix of remote sensing, but also machine learning, and especially crop health, agricultural yield. The purpose of this study, which was published later in PNAS, was to attempt to do agriculture yield for smallholder agriculture. Essentially the dominant mode of agriculture for much of the world. And in this case, we're looking at a SkySat image, so that's one of our 80 centimeter images for a portion of Ethiopia, and you're seeing the estimated yield in those crops at the end of the season. This is kind of a goofy slide, but just to sort of revisit some of the work that people have done. I don't want you to look at these particular papers, but I just wanted to stress that in this user community now, we have people working kind of all over, all different types of habitats. And it's really exciting. It's particularly exciting inside Planet to learn from these users. And I wanted to strenuously emphasize that that's why we're here today, is actually to hear from you guys, to hear from Paul and others about the kind of science you're doing, and particularly how Planet's data feed could potentially improve your science, and especially how we can, on our end, make things make things easier to plug into scientific projects and scientific work. I'm going to leave you with just a couple of teaser images that we put together in our collaboration or our early discussions with Paul. Paul let us know about some of the more exotic things happening in the Antarctic, which we were pretty unfamiliar with. So just a few weeks ago, this is January 19th, we got some images of the icebreaker outside McMurdo Station. And this, I believe, was the resupply that was taking place. So there's a ship dock there with a sort of row of containers, also at McMurdo. Michelle LaRue and I were just talking earlier today with Andrew and Paul about doing some potential penguin work here. So this is Dibble Glacier, and you said emperors probably, right? So some emperor penguin guano over here, also with the SkySat system. One of the most recent targets Paul sent me is the Italian station. I'll probably butcher the name. Zuccelli. So that's this installation right here. This image was like, totally blew me away. There's sort of this like raft of ice, and it's being carried over by the currents. I'm kind of bending off. But anyway, I wanted to end right there, hawk the website one more time, remind you guys of the postcards, and then I'd be more than happy to take any questions.
I told you it was cool. So we only have one mic working right now. So after they ask
I
the
can
question,
repeat.
just repeat it.
Yeah, I'll just repeat. Oh, or maybe this one.
Testing?
Send it back.
First off, thank you for a phenomenal talk. That was great. I had a
I can just repeat. Yeah, I'll just repeat. I might condense, but go ahead. Give me the full spirit of your question before I condense it.
Sure. The first question is easy. Is for this sort of data time series. So I was wondering if you could comment on the extent of availability of a time series sorts of type.
Great question. So the question was, what is the availability of time series of planet data? So the Rapid Eye constellation was deployed into space in 2008 and started imaging mostly in 2009. Rapid Eye was always a commercial entity, and so the density of Rapid Eye data is sort of unpredictable depending on what things were being imaged at the time. The PlanetScope, the Dove constellation, those two launches that I showed you, the first one, the larger one, took place in February of 2017, and the second one in June of 2017. So although we have older data, and especially in the orbit of the space station, we have older data back, in some cases, to 2014, 2015. There's quite a bit of data in 2016. The primary imaging, sort of our achievement of this mission one of imaging every day, essentially came online, depending on which part of the Earth you're in, somewhere between July and September of 2017. So in terms of historical data with Dove data, there's not much. There's also the fact that some of the older data is from instruments that are old enough that I just discourage people from even using it, not because it's bad data, but because it's not the same data product as what we're working with now. The sats in orbit now, these Build 13 sats, all essentially are identical, and therefore you have a much more stable product. So, but we are at daily right now. If you go to a place like Morocco, there's a solar installation that was under construction in 2017. We have easily 200 images of it, clear images of it in 2017. I mean, you could literally watch the panels go up like 5 per day over time. By comparison, if you're working in Gabon, it's a little, there's lots of clouds. Yeah.
This should work now.
Yeah, I did.
Oh, I'm sorry.
I don't want to hog the time.
It was just now more a topic question. I was wondering, in your research that you've had with universities and others, or just based on what you know from your product, is the availability of measuring reservoirs and the content of water behind a dam, is that the sort of research that you've either done or might think is possible?
Yes, definitely. Many of our disaster response activities have been either about reservoirs or about floods resulting from reservoir failures. Absolutely, our data is actually really, really good for doing water mapping. Because we have near-infrared and visible data, we can produce binary water masks with relative ease. It's not plug and play. You've got to adjust for the radiometry a little bit, but yeah, we have excellent. In fact, one of our analytics teams at Planet put together it's kind of a demonstration, but they put together a post hurricane. What was that hurricane in Houston called? Maria? Harvey. Thank you. Yeah. So after Hurricane Harvey, they actually set up a tool where you could go in and literally search by your street address and see whether you were flooded in Planet data over a given bucket of time. Now, it wasn't a fully refined, fully functional tool. It's more of a demonstration exercise, but it was really quite effective. And Planet data turned out to be great for that.
Yeah, so Steve, hold on. So you've been through about 13 or so iterations of the Dove design, and based upon your users and other feedback Planet's had over the years, what's kind of your next focus for the future Dove designs? Do you go for more spacecraft? Do you go for higher spatial resolution, spectral resolution? What's the hot item that's up next?
Great question. So there's a short list of things I can't talk about, and one of them is future sensors. However, the other thing, well, let me say about the Dove constellation, it is, we will keep the Dove-like imaging in perpetuity. So a 3.7 meter, roughly that sort of pixel size with these 4 spectral band capability is something we intend to resupply indefinitely. We actually, it's going to be even easier for us to do so than it was historically, partly due to changes in the rocket marketplace. So I don't know if you guys, do we have any Kiwis in the house? Anyone from New Zealand? This is tragic. We were just talking about how there's an extinct penguin in New Zealand that's bigger than Paul. Yep. I was in New Zealand a couple times last year. I found it to be just a delightful place. And they have a rocket company now called Rocket Lab. It's a fantastic company. They are launching a rocket that is about the size of if you remember the SpaceX Falcon 1, the first SpaceX rocket. It's a relatively small rocket, and Planet is a rocket lab. It's called the Electron rocket, and we're a customer, and we intend to be flying with them in the near future. We actually flew a single Dove satellite called Dove Pioneer on the second Electron launch, which was the first successful launch. And I got to say, for a company that's been on board 2 launch failures in just 3 years, it was pretty delightful to be on a test launch and have it make orbit, and that spacecraft is functioning healthy. I was just looking at images of it this morning, from it, not of it.
Thank you. With the amount of data over time and space, a lot of organizations are going toward cloud computing type things. And I was wondering, if Planet had plans to do something like a Google Earth Engine type platform where you can view and then also possibly process data through a cloud-based application.
Awesome question. So first of all, we're a huge user of cloud storage and cloud computing, as you guys could probably guess. I was just checking with our mission control leader a few weeks ago. Our total archive, in terms of square kilometers, is about 100 billion square kilometers. The land surface of the Earth is around 150 million. So, and that's mostly the Doves. The rapid eye portion is about 10% of that. But it's a massive amount of data. And so our data is now stored in Google Cloud Storage as part of the deal with Google. When the Terabella team came to Planet, Google became a Planet customer, and we switched all of our compute and all of our storage over to Google. In terms of how people work with Planet data, we fully anticipate and are investing heavily in the idea that much of, if not virtually all, of interaction with Planet data will take place in a cloud storage, cloud compute environment. And specifically with Earth Engine, right now there's not a direct linkage between Earth Engine and Planet. However, some of our users, in fact, one of our star users in this program, who I'm happy to say we recently hired as an intern, wrote some code that helps you shuttle Planet data over to Earth Engine. He's also a very savvy Earth Engine user. And so I would anticipate, although I can't say with certainty, that there'd be some more connective tissue between Planet and Earth Engine in the future. And you're likely to see we're investing heavily in our own analytics. So the ability to do things like bring your own data, to do processing with Planet tools, those are kinds of things you're going to see in the near future. Yeah.
I just wanted to clarify because I feel like I know the answer, but you guys shoot the ocean, right? Like in the middle of the ocean?
Good question.
Yeah?
So yes and no. We
I'm
do
glad
not.
I asked then.
Yeah, that's a great question. I'm also, by the way, I'm going to have nightmares about the giant penguin now. Z, and it's one of your faults. First of all, Planet's first mission was to image the whole land surface of the Earth. So we did not start trying to do water. We've learned that not only is there a pretty interesting market in ocean imaging, and it's especially related to ship tracking, there's also a huge market in avoiding illegal fishing. And our system is actually designed pretty well to do this. So, I mean, for instance, even though at 3.7 meter resolution, you can't identify a particular ship, with some exceptions of certain ships, you can easily see things like ships lashed together at sea, which, although not an illegal activity in its own right, might be an indicator of possible illegal activity. And when you combine that with AIS data, ship tracking data, then you potentially get another piece of information there. So we have, over the last year or so, began to set up certain open water regions where we are imaging full-time at the same level as the land. Those were sort of custom, so we could start to explore how this works. There was another challenge, which is there's no features in the ocean except for these ships, potentially, and our image processing chain is set up in such a way where rectification to the Earth's surface is a critical component. So we had to design a way to essentially produce an interpolated image. And we use a mix of our star tracking camera on the Dove spacecraft, and because we collect our images in a long chain, there are often land images in the chain, so we can rectify those and then essentially interpolate the position or adjust the position of the other images. And if you're now using Planet Explorer, there's actually a little toggle in one of our filters that sets whether you can see images that lack or do not lack, that have or don't have ground lock at a certain ground control point threshold. But to answer the most important part of your question, at present, no, we're not imaging the ocean in mass. We're imaging a few major regions of ocean, especially areas where there's a lot of water around coral reefs, for example, where there tends to be a lot of fishing activity. In our discussions with our own mission control team about what we could be doing in the poles, we're quite keen on potentially doing open water imaging over the poles. Interestingly, because we have such a great challenge of rectifying polar imagery anyway, we're going to use the technique that I described to you for open water as a starter technique for a lot of the polar imaging anyway. So it's likely you're going to get the water with the land, but we got to figure out some stuff. Yeah.
So, I mean, this probably might be heretic in this crowd to ask this question, but what about sensors looking the other way? There's a lot of interesting science that could be done, say, looking at the sun, for example. Is that in your plans? Are you not allowed to say?
Well, I can't talk about those plans. I will say you startled me for a moment because there is something that's really bad, which is looking sideways, which essentially nobody's licensed to do. And it has to do with proximity awareness from satellite to satellite. You can imagine if you got $1 billion or multi-billion-dollar satellite asset and the ability of a university CubeSat to take a picture of it, it would be a problem. So as far as imaging into space, I'm not aware of any specific things we're doing. I will say our founders and the most of the earliest employees of the company come from not classic aerospace, but come from a place of deep enthusiasm for space exploration, for space settlement. In the earliest days of the company, Andrew was there at a function that we ran with Forrest Stearns, our art director, and some other people, specifically focused on lunar settlement. The whole company was essentially trying to figure out how we could, build lunar colonies. I personally am one of these people as well. I took a day off to go watch the Falcon Heavy launch in person a couple weeks ago. So I think if the opportunity presents itself, that almost certainly would be something we'd love to do. I think the one in the back was, yeah.
Okay, thank you for the great talk. My question is, I know you don't want to talk about future sensors, but what is your opinion about commercial remote sensing image providers going into hyperspectral imagery and sensing? Because there isn't a lot of that currently.
I will say that all things are possible, and I mentioned, there was a moment I was talking about sensor interoperability or being sensor agnostic. So the LAI example, which I admit is was a little bit mangled. It shows you the power of having two different sensors with two different spectral capabilities that don't have the same spatial or temporal abilities. And that suggests to me that hyperspectral could be extraordinarily powerful even if there were relatively few sensors. That is, imagine, for example, you have a single hyperspectral observation. Let's say, for the sake of argument, it's an aircraft observation. And you have a simultaneous retrieval from space, maybe from the Doves, maybe from Sentinel. Your ability to produce algorithms and local modeling type analyses that can allow you to learn things that only the hyperspectral sensor would seem to know, but essentially predict them from the other sensor is really powerful and potentially one of the most interesting things that I think will happen in remote sensing in the near future. On the LAI thing, another example of that is a little better, although they haven't published it, so it's not quite as good. The same group attempted to do the same thing with thermal. So they took the Landsat thermal observations of these fields and tried to predict soil temperature with planet data after a modeling exercise where they linked the Landsat thermal and the planet resolution data. And they did a pretty good job. And you'd think to yourself, like, how does that doesn't seem possible. But you know, when a soil surface, if it's wetted, is going to produce a different visible signal, and that's going to have a huge effect on its thermal state. And so you're not going to know it exactly, but they're able to pick up these visible cues and near-infrared cues that are related to these other things. So yeah, I think it's a total yes, and it's probably going to be one of the most interesting areas of research, not just in commercial remote sensing, but in remote sensing generally moving forward. I mean, there's so many sensors. Here I just described we're operating the largest constellation of satellites in history. But if you look at the chart of overall satellite deployments, it's like a hockey stick. So I think, yeah.
Yeah, Joe, you touched on this a little bit, but get into a little bit more detail on the sensors, like the evolution. I think you were like bare patterns. Was it CCDs or CMOSs originally with 8-bit?
That's.
I don't remember what it
Yeah,
was.
that's a question.
But what are you at today in terms of the, also the resolution? You had 12, 16-bit, whatever.
Yeah.
And it's a bare pattern, I'm guessing.
Yep.
Still. Yep.
Yeah, it's a Bayer mask. So it's a 12-bit sensor. It's a CCD. It's a 6600 by 4400 pixel sensor. What we do is, actually, let me see if, just to have something up there. So this is a pretty old look at some of our images, but it works for this. So what's highlighted here is only the visible portion of the frame. These are other visible frames shown in blue, so there's a little overlap here. What you're not seeing is the near-infrared data. And it actually is the case that for this image, this is only half the CCD. So this is 6600 by 2200 pixels. The near-infrared data is here. And we produce a band-aligned 4-band product by taking the near-infrared data from the adjacent frame and aligning it to this one. It's a 12-bit sensor. Some of the radiometric challenges are that and I don't know if I am a remote sensing scientist, but I was more of a LiDAR person, so apologies if I use the wrong jargon here. You guys can actually correct me. The radiometric purity of each spectral band is not as good as, say, Landsat or Sentinel. So there is the possibility, for example, if you're a photon in red light, actually green and blue is better. That's where we have a bigger issue. If you're a blue photon, there's a decent chance you end up in our green channel versus the blue channel.
Yeah, if you're using like Kodak chips, and I don't know what you're using, but they have their spectral curves, and you'll see that bleed over.
Right.
In which the related question is, what's the shutter? Is it electronic shutter? I'm trying to remember the term.
That I don't know. I can investigate and get back to you. I'm not.
It's not critical.
We do use shutter. Yeah, I mean, we use a thing called time-delayed integration. So one of the coolest things about how that camera works, I mean, a lot of other sensors do this too, but we're moving at orbital velocity, and we need to deposit photons on the CCD. So when we open the shutter, it's a very short prospect before we smear and get motion blur, right? So time-delayed integration is essentially in the along track direction is storing photons from the same location, even though the satellite is moving, into the same pixel, so sort of well on the sensor. There's a two-way filter that we use to split visible and near-infrared light. And then we use a Bayer mask to deposit colors onto the CCD as well.
So how about, do we have one more question, and then we'll call it a day, or Mike?
I'm just kind of curious, how closely integrated are these different classes of satellites that you operate? Are they operated independently from each other, or is there like tip and cue capabilities that you're actively doing with these, or are the different teams working on these in different capacities? And I guess the follow-on to that is there a lot of academic or research potential in that, or is that more for other markets?
Great question. Our sensors and spacecraft all have essentially totally separate origins. However, our mission teams and operations teams work very closely. Now, that being said, there are people dedicated, for example, to mission control for SkySat alone. But they work within a large mission control team that manages and has visibility across the different sensors and can optimize the different constellations to address the kinds of things you just described. One of our, let me tell you, a core benefit of the acquisition of the Terabella team and the SkySats into Planet is the combination of passive, unbiased monitoring of the Earth's surface with the possibility of, in an automated way, queuing a high-resolution asset to take a picture. Let's take the example of the ship tracking. With a mix of images, suppose you write a machine learning algorithm to look at barrels of images of the ocean, and all you're looking for are two ships together at sea. Then you intersect that with an AIS ship tracking database and say, now only give me the ones where one of the two ships is not broadcasting an AIS signal. Now, in our reality, that's probably actually still too big of a list. But suffice it to say, that allows you to cull the list of possible interesting targets for illegal fishing. And in an automated fashion, you point a high-resolution asset and take a closer look at those ships. And with the SkySat, you can actually potentially certainly identify the type of vessel. And in some cases, you may be able to use markings to identify the specific vessel involved. And so that chain is something that the ship tracking is just one example. There's many other examples where you would do that. But that's absolutely one of the core concepts that our mission control and tasking teams are working toward. Yeah.
How about one more?
Excuse me. I guess my question is, can you do the same thing you were talking about for aviation, particularly large jetliners?
Track airplanes and take pictures?
I'm thinking the missing one.
You're talking in
MHS.
flight?
Now, that you weren't up at the time.
No.
But for investigation purposes down the road.
That's actually an example where, although you certainly would do the same thought process of queuing a high-resolution asset, you may not even need, the short answer is yes. I mean, you can imagine the Planescope constellation, if you tweak that CNN algorithm to look for ambiguous objects in the sea rather than vessels specifically, then you would do the same type of operation. Depending on the search area involved in a search and rescue operation like that, you may not even need that level of automation. You may simply say, we have a search area, there's an emergency, we're just going to task it all and look at it all. In fact, I mean, one of the examples of an illegal fishing event that was essentially caught in the act was the result of a single tip from an AP reporter. And this was a digital globe image of a particular ship lashed together at sea that turned out to be a slave ship. And that just came from a single tip from a reporter. So I think, thank you guys so much. I really appreciate it.
And thank you all for coming, and I highly recommend that you go sign up and start looking at it right now. This is here.